Hello, this section is on section 1.1, 4 ways to represent a function. First thing to talk about is what is a function? A function is just a rule that relates a first group to one and only one value in the second group. So it's very important this one and only one value. That's what makes something a function. You can't have two things going to this one number going to different places. You have to know exactly where they're going. The first group is called the domain. So it's usually a set of values. And the second group is called the range. A lot of times in mathematics, we deal with variables, we deal with unknowns. Variables are just things that are unknown that we're trying to find. They're values that can change, and we're trying to find them. And there are two different variables in mathematics that we usually deal with. One is called the independent variable. This is the values, this is a variable that represents the first group. And you pick this one. So this is the one you get to actually choose which value you want to work with and then go from there. The dependent variable is a variable that represents the second group. Again, a variable is just something that you use to represent an unknown quantity or a value. We look at functions lots of different ways. Here's an example of one. Here's a function. These are actually two different functions. There's function g, which is the blue line. And there's function f, which is the red line. An example would be you might do f of -4. So remember, f of -4 means you want to find the function value at -4. -4 is the value from the domain, because those are the numbers that go inside. And we're looking for the range value. So we come up here to the graph. We come over here to -4. -1, -2, -3, -4, and then we go down, in this case, to where f is. So in this case, it'd be right there, and that value represents as -2. So we would say that this value is equal to -2. Same thing if I want to find g of 3. G of 3 means I'm using the g function instead of the f function. 3 again is the domain value is 3. It's the value of the independent variable. So I come over here to 3 on this axis, and I go up until I find out what that g value is. So when I come up here, I can see that's 1, 2, 3, 4. So g of 3 is the number 4. If I want to know like what values of x for which the f of x equals g of x, you're looking for where they intersect. What are the values where they actually cross each other, basically? So I'm going to pick a different color here just for the fun of it. Okay, so here's my different color, and I'm going to look for where they intersect. So if I look along here and I come along G, I see that G and F have the same value right here. And that X value, where that happens, is -2. So one answer here for this is the X is equal to -2. Now, it doesn't have to be, that's not the only place where they cross. So if we keep, again, moving along G, if I keep moving along G, I notice, hey, G and F then intersect here at this point too. And that happens to have an X value of 2. I don't care what the Y value is. I care in a way of what the Y value is because that's what they both correspond to the same Y value. But what I'm caring more about is that they cross each other at that point. So I want to know that x value. So x equals -2 and x equals 2. And then I might want to estimate the solution to the equation f of x equals -1. So in other words, I'm going to come down here and I'm going to pick a different color. I'm going to come down here -1, and I'm basically thinking of having a line here that goes across, and I'm looking to see where does it intersect the graph of f. I notice it doesn't intersect the graph of g, but it does intersect the graph of f, intersects the graph of f right here. So f is equal to -1 at the value of -1, -2, -3. So when x equals -3, f is going to equal -1. And the last thing is, what value is f decreasing? Decreasing means it's going down. So if you think about this, you're moving along the graph, you're coming along f, you're going up. Think of it as you're going up a hill. So I'm going up, 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 up a hill. I'm climbing to the top of my hill, and then here I get to the top of my hill, and then I'm going to start going down. Think of this as a great ski run. I can go down. So in that case, or a nice bike ride down. So that happens at an x value. Again, we're looking for what x values this happens. That starts at x equals 0, and then it keeps going. We don't know if the graph keeps going beyond here, but we can assume it does. So we can say it starts at x equals 0 and keeps going to x equals infinity. So we would say that it decreases on the interval from 0 to infinity. Another thought, another way to look at functions is we can look at functions in terms of data. So here we have temperature readings. T were recorded every 2 hours from 2 p.m. in Baltimore on September, from midnight to 2 p.m. In Baltimore on September 26, 2007. The times were measured in hours from midnight. So in other words, 0 means it's midnight, 2 means it's 2 in the morning, 4 in the morning, 6 in the morning, 8 in the morning, 10 in the morning, noon, and then 2 o'clock in the afternoon. And these are my temperatures. So what I'd like to do is I'd like to use the readings to sketch a rough graph of this. We're going to actually use Desmos to do this. We're not going to do this by hand. We're going to actually you can do it by hand, but your graph won't be very good. So we're going to actually use Desmos to do this. So here's Desmos. And in Desmos, we're here doing a graph, and I'm going to go ahead and do a table. So my table values, if I look at those values again, I had the values of 0, 2, 4, 6, 8, 10, 12. Desmos is pretty smart because it knows that's what I'm doing, and so it starts filling them in for me. And then my y values are going to be 68, 65, 63, 63, oops, 65, 76, 85, and 91. Now I'd like to be able to see the graph of this. Unfortunately, my graph goes from 0 to 10 and 0 to 10, so I'm not going to see those because I'm going all the way up here to 68. So I need to change my window. If I come over here to this little, looks like a wrench, it's graph settings. I can now change my window. I'm going to start my y-axis 0, and I'm going to go all the way up to, well, my highest value was 76, so I'll probably go up to 80. I'm sorry, the highest value is 91, so I'm going to go up to 95, let's say. And then I can see my dots now. And so that actually lets me see that. Oh, and I realized I need to change my x-axis also. We don't need to start at -10. We can actually start it at 0 and maybe go over to 16 just so we can see all the dots. And so now I can see my graph. Here's my dots, here's my graph. And this is another way to represent a function. So I can get this. I can go ahead and do a screen grab and plug this into my values. They do want me to find out, to estimate the temperature at time 11 o'clock. So remember, this is midnight, 2, 4, 6, 8, 10, 12. So 11 o'clock is somewhere in between. I can actually draw a graph on here. I can actually fit this curve. There's a way to make Desmos actually fit the curves, but I'm going to see if I can't actually just draw it in there No, I can't actually draw it in there. So there's a way to actually get it to graph with these. Right now, we're not going to do that. But if you think about having a curve here and just connect the dots, you can see that at 11 o'clock, it looks like it's about 80 degrees. So we can now say that it's 80 degrees for that. And you can actually put this graph, you can actually do a screen grab of the graph and you can put it in the notes. All right, so that's another way to represent functions and deal with it. So this is actually where I want to start talking about representing functions. We actually represented functions in 3 out of the 4 ways with this example. So the way we represent functions is we represent functions we saw them, we actually represented them numerically. Where we had a data, that was the last example. We can represent them graphically, which is also the very first example we did that with graphs. We had 2 graphs on that. We can also represent them verbally. And we can represent them algebraically. So as I said, we actually did do that with all of these, except for the last one, algebraically. We did represent them numerically, we did represent them graphically, and we talked about verbally. So to go back and just show you, this first graph here, this is a graphical representation of my functions. So this is a way to graphically represent them. This, we had a verbal representation of it, where we talked about what we did. We can also have a different verbal, I'll do a different one later, but we also had numerically, this was the data. And so a verbal one could also be where you talk about the price of mailing a stamp, and you can talk about how expensive it is to mail not a stamp, but a letter, and it's up to a certain weight. So up to an ounce, it costs a certain amount, and then above that, it costs a different amount for every extra ounce you add on. And so that's another way to talk about it verbally. Algebraically is the only one we really haven't mentioned. And so I kind of want to talk about it. That's the one you're used to, but I want to make sure you understand that all of these are functions. They're all ways to represent it. They're all ways to get a value and look at a function. So don't think of functions as always being algebraically. Numerically and graphically and verbally are perfect representations of functions, and you will be working with them a lot. But algebraically would be something like f of x equals 3x squared plus 5x. So that's an algebraic. We get a lot of algebraics from our data. So actually, if I went back to Desmos, I could in fact fit this. This looks kind of like an exponential. So I could actually fit it with an exponential. And so I can say y1 is, I use this thing called a tilde. And exponentially means you're going to have some value to the x1. And it should have graphed a little bit better than that. I don't know why it didn't. But that's, you can do that kind of stuff and you can see what your parameters are, what your A value is. So it didn't fit it very perfectly, but we can actually do regression analysis in statistics classes and do a better fit of this and get a better idea of what it might look like. So you can actually graph these up. Let's add in another parameter. Yeah, there we go. That's a better one. If we add in a B, that will shift it up and we can now see a little bit better. And that allows us to fit this data to this graph. So that's another thing you can do, is you can fit graphs to these. All right, one more concept that I want to give you is this idea of a piecewise function. A piecewise function is where it's defined differently during different places. So during different x values. So here, between x is greater than or equal to 1, it's defined as 2x plus 3. And when x is less than 1, it's defined as x squared minus 1. So we can actually graph this. And I'm going to go ahead and just do a sketch of a graph. So I'm going to draw a coordinate plane first. Whoops. I know I need x equals 1, 2, 3, 4, 1, 2, 3. I'm plugging around that space here. 4, 5, -1, -2, -3. So the main thing to realize is that x equals 1 is your kind of change point. So when we're greater than 1, we're the function 2x plus 3. So if you think about it, at 1, you're going to get 5. And above 1, you're going to be going up with a slope of 2. So you go over 1 and up 2, and you get this here. And so you get a graph that starts at that point and goes on up. But if you're less than 1, you're no longer this function. You're now x squared minus 1. So instead, we're going to graph that during this x is less than 1. So again, just kind of thinking about plotting points. If x equals 0, you're down here at -1. If x equals 1, you're going to be up here at 0. But you can't, remember, functions can only have one value. So I can't say that x equals 1, the number 5 and the number 0. But I do notice it's just less than. So it comes up to 1, but not hitting it. So we do an open circle there. And then we're going to go through that and then go up from there, because it looks like a quadratic. So there's your piecewise function, graphing it up. We do a lot of piecewise functions in calculus. So just want to make sure you know them well. A couple other piecewise functions that exist is the absolute value function. The absolute value function is f of x equals x, the absolute value of x. You know it as that, but if you actually want to look at this as a function and graph it, it actually is a piecewise function. If x is greater than 0 or equal to 0, then you just get the number back, right? So if you put in 2, you get 2 back. If you put in 5, you get 5 back. If you put 0, you get 0 back. However, if you're less than 0, you get the opposite number back. If you put in -1, you get 1 back. If you put in -2, you get 2 back. So the way we represent that is a negative in front of the x. Changes the sign. So there's another piecewise function. Another piecewise function is what is called the greatest integer function. You have not probably seen this function. The greatest integer function, the way we write it, it kind of looks a little different. It's represented like that. And this is known as the greatest integer function. And what it means is it is a piecewise function. And actually, I'm not going to write it as piecewise because it's a little hard to write this as a piecewise. But it basically is that you get a value, your answer is going to be a value that is less than, it's the greatest integer that's less than that value. So if you did f of 2.1, the greatest integer, actually I should have put 2.1 in there. The greatest integer less than 2.1 is 2. If you did f of 1.9, the greatest integer less than 1.9 is 1. Now, what is interesting is what actually happens at the intersections, at the actual values right at when it actually is 1. So, all right, so that would be, it actually isn't just less than x, it is less than or equal to x. So I just was checking on that. So it's less than or equal to x. So in other words, if you wanted f of 2, the greatest integer less than or equal to 2 is, of course, 2. So just one more, the greatest integer, if we wanted f of -1.3, the greatest integer less than negative 1.3 is not negative 1, it's negative 2. That's the greatest integer that's less than or equal to negative 1.3, so it's negative 2. The graph of the greatest integer function is a little different. So just drawing this out. It's always good to label your values. So if I'm between 0 and 1, I'm going to be 0. So if I give you any value between 0 and 1, I'm going to give you 0. But at 1, I'm jumping up here to 1. So that's why I put an open dot here. And between 1 and 2, I'm always going to give you back the value 1. And but then at 2, I jump up here to 2. And at 2, 3, I'm going to always give you back the value 2. And so forth. And if come over here, if I give you between negative 1 and 0, I'm always going to give you the value negative 1 up to 0. And here at negative 2, this is known as a step function because it looks like a pair of stairs. So that's what this one does. And one last concept I just want to mention is increasing and decreasing functions. So a function is increasing, f is increasing, if f of x1 is less than f of x2 for x1 less than x2. In other words, the numbers are getting bigger. Your y values are getting bigger. F is decreasing if f of x1 is greater than f of x2 for x1 less than x2. In other words, as x gets bigger, your y values are getting smaller. So let's just state on what intervals the function is increasing and decreasing. So from here I can see I'm going up. So again, think of it as increasing means you're going up on your graph. So from 0 to 1, I'm increasing. I'm sorry, it's not 0. I don't know why I just said that. From 1 to 2, I'm increasing. I also noticed that I have a dot here. That means I don't have an arrow, I have a dot. So that means I'm actually starting there. It's a closed dot, so I have a closed bracket. From 1 to 2, I'm increasing. Now at 2, I don't really know what I'm doing, so I'm not going to include 2. So I'm going to put an open bracket to say I'm not including that one. And then I'm going down. And when do I change again? It's at 5. So I'm unioning this with from 5. And then I'm going up, and notice that there's an arrow here, so I'm assuming it's going to keep going up. So I'm going up from 5 to infinity. Infinity, again, you never include, so it's always going to be open. So we're increasing there. And we're decreasing. Again, where were we going down? Well, we were going down from 2 to 5. Again, we don't include the endpoints because we don't really know what's happening at the endpoints. And that's kind of your brief introduction to functions.